In this example, we will see how to apply node voltage method to a circuit containing a dependent source and how to deal with the resulting supernode. In this circuit, the dependent source is highlighted here. We can see that there is a minus and plus inside the symbol. So that means this dependent source is a voltage source. And we can see that the magnitude of this component is in terms of a current. So that means this component is a current controlled dependent source, CCVS. Let's apply a node voltage method to this circuit. So we need to identify essential nodes where 3 or more circuit elements meet. So in this circuit we have 1, 2, 3, and this whole bottom conductor is one essential node. Step 2 is to select a reference node, and in this case we can ground the bottom essential node. Now we need to check for supernode. So a supernode occurs when a voltage source, whether independent or dependent, is connected between two reference nodes. If we look at this independent voltage source, this is connected between the reference node and this essential node. So this voltage source does not cause a supernode, but this dependent voltage source is connected between two essential nodes. So this dependent source will cause a supernode. So in order to apply the node voltage method, let's first label the nodes. So we have node V1, V2, and V3. We can see that since this voltage source is directly connected between ground and node V1 has a voltage 50 volts with respect to ground. So this means we do not need to apply Kirchhoff current law at node V1. So this leaves node V2 and V3, and these nodes along with the dependent source form a supernode. So we treat these two nodes as a single node and apply Kirchhoff current law to the supernode. So we assume all branch currents are flowing away from the node. So on this side of the supernode we have two branch currents, and then on this side of the supernode we again have two branch currents. So we mark all the branch currents flowing away from the node, and now we are ready to apply Kirchhoff current law to the supernode. So Kirchhoff current law states sum of currents entering a node is equal to sum of currents leaving a node. So starting with this branch current through the 50 ohm node, this branch current is given by V2 minus 0 over 50. And then this branch current through the 5 ohm resistor is given by voltage on this side minus voltage on this side, which is 50, divided by the resistance. So this gives V2 minus 0 over minus 50 over 5. Now moving to the other side, this branch current through the 100 ohm resistor is V3 minus 0 over 100. And then in this branch, the current magnitude has to be equal to the current source magnitude. And since this branch current is in opposite direction to the current source, we get minus 4 is equal to 0. The next step is to write the supernode constraint equation. And in order to write the supernode constraint equation, we need to apply Kirchhoff voltage law to the supernode. Recall that node voltages are defined as voltage rise with respect to ground. So this supernode can be redrawn as follows. We can represent V2 as follows. So we can represent V2 as a positive voltage with respect to ground, and then we have the dependent current controlled voltage source, magnitude 10I phi, and then we can represent V3 as a positive voltage with respect to ground, and this gives us the circuit to which we will apply Kirchhoff voltage law. Now the direction of the current does not matter. We can assume clockwise or anti-clockwise. Suppose we assume this current direction. Now in order to apply Kirchhoff voltage law, we start here. So for V2 we are going from minus to plus. So this is a voltage rise, and we write it with a minus sign in accordance with the passive sign convention. So this gives minus V2. Going from minus to plus is another voltage rise. So we get minus 10I phi. And finally, going from plus to minus is a voltage drop. And we use a positive sign for voltage drop. So we get plus V3 is equal to 0. So this shows the process of applying Kirchhoff voltage law to the supernode to get the supernode constraint equation. After dealing with the supernode, next we need to write the dependent source constraint equation. What that means is we need to express the controlling variable I phi in terms of the node voltages. I phi is shown here. This is the current through the 5 ohm resistor in this direction. So we can write the dependent source constraint equation by applying Ohm's law to this resistor. And this gives I phi is given by, we follow the direction of I phi. So this is V2 minus 50 over 5. So what we get is V2 minus 50 over 5. So we can see that here we have 3 unknown variables, V2, V3 and I phi, and 3 equations, and we can solve these equations using any known method. We can use Mathematica to solve these 3 equations, and using the solve command we can obtain the node voltages and I phi solution as shown here. So we can show that the obtained solution is V2 is equal to 60 volts, V3 is 80 volts, and I phi is 2 amps. The final step is to solve for the circuit variables, and in this case we have to solve for the power associated with the current source. We can see that the voltage drop across the current source is the node voltage V3, because this current source is connected between ground and node 3. So using the fact that node voltages are a voltage rise with respect to ground, we can associate this polarity of the voltage drop across the current source. Now the power associated with the current source is the product of the voltage, which is V3, and the current, which is 4 amps. We need to use passive sign convention to decide the sign of the power calculation. In this case, we can see that the current is entering the terminal marked minus. So we associate a minus sign with the power calculation. Now substituting values, we get minus 320 watts. So the final answer is negative, and this means that in accordance with the passive sign convention, this current source is supplying power to this circuit. We can verify our solution using PSPICE. In PSPICE, the current control voltage source is available as path name hpoly, and here we are using the bubble paths to facilitate in the connection of this component. So simulating, we can show that the node voltages are 60 volts and 80 volts, and the current I phi is 2 amps. We can also use LTSPICE to simulate this circuit. This is the circuit constructed in LTSPICE, and we're using a VTest source to help configure the current control voltage source in LTSPICE. And if I simulate, we can see that the node voltages are 60 volts and 80 volts, and the power dissipated in the current source is minus 320 watts, shown in the bottom left corner of the screen, and this confirms the solution.